So this lesson, I'm going to divide this lesson into three parts. This lesson is from section 7.8. It's on improper integrals. So thus far, we've looked at integrals. We've looked at integrals that satisfy these two conditions. First of all, that the interval of integration from a to b was finite. So that's important, right? We're going from some point to some point. And the other one is that the functions being integrated were continuous. Um, Improper integrals are definite integrals for which one or both of these conditions do not hold. So in this lesson, we're going to look at how we can use limits to evaluate these integrals. So we're going to use the stuff we did in the last section with L'Hopital, talking about limits, but we're going to pass that on and now apply these limits to integrals because these integrals are going to be a little bit weird. All right, so first, just to start out with, and just something to think about to begin with, compare these two integrals. One be the integral from 1 to infinity of x dx. The other will be the integral from 1 to infinity of 1 over x squared dx. So these are both cases of improper integrals because they do not have finite intervals of integration. Right, we're going from 1 to infinity. We can see they're very different. First of all, look at this one. So we're integrating f of x equals x from 1 to infinity. So 1 is here. So we're looking at the area under the curve, under this curve here, from 1 all the way out forever. Okay, well, you can see what's going to happen, right? I mean, it's pretty obvious that as I keep going out this way, this area under here is just going to get bigger and bigger and bigger. And so we would expect that this integral is going to be infinitely big, right? The integral from 1 to infinity of x is just going to be infinitely large, which is not super interesting. On the other hand, look at this integral here. And I'm going the integral from 1 to infinity of 1 over x squared. So here's g of x is 1 over x squared. Here's 1. And we're taking this area underneath. This pen is a little bit, this thing is not calibrated great, but that's all right. We'll manage. We're looking at that area under the curve, and we can at least wonder, well, this area, as I keep going on and on towards infinity, what I'm adding to that area is getting smaller and smaller and smaller. So so what I'm adding to this integral as I extend x out this way is less and less and less, to the point where we might wonder if there's some sort of limit there. Is there some point at which, like, is there some maximum that this integral will approach but never reach? Another way to get your head around this, and this might be confusing, so if it confuses you, just pretend it didn't happen. We could actually graph the value of the integral as x gets from, so say, take the integral of we'll call this function big F of x, the integral from 1 to x of t dt. So we're taking that same function, the linear y equals x function, but now what this graph is going to show us is the value of the integral from 1 to some value of x. So from 1 to 1 right here, it's going to be 0, right? Because that's going to be no area. That's going to be nothing. So from 1 to 2, the value of the integral is going to be somewhere around here. So that's saying that, the value from 1 to 2, that's saying that this area in here is somewhere between 2 and 3. Or no, between 1 and 2, I mean. Right? And as I get farther, if I go from 1 to 3, the value of the integral gets bigger. The value of the integral from 1 to 4 is even bigger, and you can see where this is going here, right? It's pretty clearly it's a quadratic curve, right? It's a parabola. It's going to keep getting bigger. So the farther out I go along x, as I take the integral from 1 to increasingly larger points out there on the x-axis, the value of the integral just keeps going up and up and up. Contrast that with this one. So this is a function big G of x, which is the integral from 1 to x of 1 over t squared dt. So I've taken that same function, 1 over x squared, but now I'm asking what's the value of the integral from 1 to x as x gets bigger and bigger and bigger. And you can sort of see what happens here, that as I keep going out here, right, the integral at 1, from 1 to 1, obviously it's just going to be 0. From 1 to 2, it's going to be, the value of the integral is going to be somewhere around a half. So that's saying, again, that, let me erase some of this stuff here. The integral from 1 to, say, 2, that this area, that's telling me that this area under the curve in here is going to be around a half, right, around a half here. And then as it gets bigger and bigger and bigger, it goes on this way. And what happens is that it looks like, and we can't say for sure, but just looking at the graph, it looks like there's an asymptote here around y equals 1. So that we could say that as this x goes to infinity, it looks like the value of this integral is just going to be 1, which is interesting. So what we might expect when we look at this sort of improper integral when we're going from some number to infinity is that, well, the value of the integral is going to be infinite, right? Because you're thinking of this case, right? It's just going to get bigger and bigger and bigger. But there are going to be cases where at least it seems possible that that area under the curve is going to approach some sort of limit. And you can see that sort of graphically here in the asymptote that this graph appears to approach. Now, what did we just do? Well, we said we're kind of interested in what's this asymptote? Is there an asymptote here? Well, what we're asking is there a limit to this function g of x? Because remember, that's what we graphed here. This is g of x. So we're asking what happens as x goes to infinity to this function big G of x. Well, g of x, I said, was the integral from 1 to x of 1 over t squared dt. So we're asking about the limit as x goes to infinity of the integral 1 to x of 1 over t squared dt. Well, we can actually figure out what this is, and we just use our sort of familiar techniques of integration. Just forget for a minute that this limit of x as x goes to infinity is even there. How would I integrate this? Well, this is going to be, this is t to the negative 2, so the integral will be negative 1 over t. The antiderivative of 1 over t squared is negative 1 over t, and I'm going from 1 to x. Okay, so what can I do then? Okay, well, that's limit as x goes to infinity. Just treat this like you had pretend you had a number here. You know, if that was 5, what would you do? You'd say, oh, negative 1 over whatever this number is, so I'll just put x, minus negative 1 over 1. Right? That's how we evaluate definite integrals. Okay, well, what's going to happen here? Let's just clean this up a little bit. X goes to infinity of negative 1 over x plus 1. Now, this is pretty easy. This is a really easy limit. Now we've got limit as x goes to infinity. Well, as x goes to infinity, this term here is just going to be 0, and we're going to be left with what we thought, 1. Right? We said that would look like the asymptote in this function. It looks like this is what happens to this integral as x goes out towards infinity, and in fact, we've just shown algebraically that that's what happens. So this is a way of evaluating these indefinite integrals, right? If I want to know what the integral from 1 to infinity of 1 over x squared, I could say, well, what's the limit from 1 to some variable here? If some variable approaches infinity, of the integral of 1 to that variable over 1 over x squared dx. Let me give you another idea. Now, let's compare what happens if we did that with the other function. The first function we had, which was the f of x, that was just that straight linear function, y equals x. And I said, well, we can sort of imagine we can create a function, big F of x, which gives us the value of the integral from 1 to some value x. And we can apply the same limit thing here. We can apply the same limit idea here. Well, what happens? We get limit x goes to infinity of the integral from 1 to x of t. So the antiderivative of t is going to be 1/2 t squared. And we're going from 1 to x again. Now, limit. Okay, and when we do that, what do we do? Well, we'd say 1/2 x squared minus 1/2 times 1 squared. And where's my thing here? Yeah, that's what I'm looking for. Right, so I've got the limit as x goes to infinity of, well, I've got x squared over 2 minus 1/2. And obviously, as x goes to infinity here, well, this thing is going to become infinitely large, infinity squared over 2. It's going to get bigger and bigger and bigger. And the farther I go, the bigger it's going to get. So it's going to just approach infinity. And that's what we thought was going to happen, actually, right? When we said, even when we just looked at the first thing, we just looked at y equals x, we said, well, as I go farther and farther in this direction, right, farther and farther along the x-axis, the value of this area under the curve is going to get bigger and bigger and bigger. So as x goes to infinity, the area is going to go to infinity. So as x goes to infinity, the value of this integral is going to go to infinity. So this one we thought would end up being infinitely large, and that's what we saw. So this is what we've done. We've got a strategy here mapped out for how to, and we'll talk about it a little more in the next video, but I wanted to get to the conceptual part down at the beginning. We've got a strategy for how to evaluate these sorts of improper integrals where we've got an integral of, where one of the endpoints of one of the limits of integration is not finite. Now, I'm going to talk briefly about what we saw here, and just to sum this up before I go, I'll make another video to talk about the other stuff, but to do some of the problems more in depth. But here, convergent versus divergent improper integrals. This is important. So this is important terminology here. We saw these two intervals here, right? We said this integral here, the integral of this integral, right, of this function y equals x as 1 goes to infinity. We said it goes on forever, and it just gets bigger and bigger and bigger. It doesn't approach some particular number. We call that a divergent. Isn't that a movie or something? Anyway, divergent integral, improper integral. So it doesn't really give us any answer. Like we try to figure out what the integral from 1 to infinity of x dx is. We don't really get anything. On the other hand, this one, 1 to infinity, the integral of 1 to infinity of 1 over x squared dx, it does get somewhere, right? It actually approaches a number, and we said as we go out to x, the value of that integral approaches 1. So we can say that this integral, we said it was equal to 1, and so because we've got some concrete answer there, we can say that the integral, that is a finite answer, we can say that that integral is convergent. It converges on 1. Sometimes the limit won't exist. Sometimes, which is to say it'll be infinity or something. Then there's no answer to what that integral equals. We say it's divergent. Sometimes it will give us the limit that we set up will give us some concrete finite answer. That means that the limit is convergent. That this is going to happen is sometimes it's obvious when you look at the graphs, but you can sort of see it now. We've also done it mathematically. All right. In the next video, I'll go over some examples and sort of talk about how to deal with some particular cases, and then I'll do another video about a different kind of improper integral.